good morning for Indonesia and maybe good evening and good afternoon for other region. So welcome back again to the second session of today's lecture. Dr. Budi will explain more about the antibody simulation and maybe some advanced topic. So please.
Thank you, Ibnu. I hope my voice is very well. Let us continue with, at the end of this lecture, we will be together try to collect astronomical data related to small bodies. Now, I will continue to the model. We have phenomena, we have mathematical model, so we can put the numerical methods. The concept, the main concept, we focus on the force, the equation that I display in the slide. The force in the left side equal to blah blah blah. So we need to calculate the right hand side for the force in acting in the system that we want to know. Both can be the future or the past. And the second, time evolution. So it can be the future we want to know or the past. For example, we have the suggested meteor crater in Bangka Street. Some of you from Belitung or Bangka? No? Oh, you may know the black stone. No? You familiar with black stone? From our colleague in geology says that the black stone can be originated from the impact with very high velocity in very high pressure. So if you look to the map of the Bangka Island, close to the Sumatra part, usually the island and the part of the big island will have the same pattern. But the Bangka Street, you will see the big, such as a big circle. So maybe you can propose some expedition to dig the strait to collect some sample. So if we trace back to the past, we can know when the crater was happened. This time evolution. But we need a model first. Now, classical algorithm The classical one, you focus on gravitational force plus many things, for example, non-gravitational and others. So you discretize the time evolution, for example, for step 1 day or 1 minute, for example, it depends on your case, or 1 year or 10 years, step by step. So you propagate the time evolution. Each time you will have the 6 orbital elements, and for the next time you will have the 6 also orbital elements, and so on. For a single object, for example, a planet or for small bodies. So if in your system you have, say, 100 objects, including 9 planets, 1 for the sun, 9 main objects, including the sun, and 400 small bodies. So each object will have a 6 orbital element, a set of 6 orbital elements. So for example, if you have 500 objects in the system, you will have 500 orbital elements for one time evolution. T0, T1, T2, and so on. 500, 500, 500, 500. So the first one, you need the initial values. The 500 initial values of your orbital elements. Theoretically, the number of calculation, if you have 500, you will have for each type 500 times 999 calculation for each type, each step. Usually, you can put as initial values Cartesian coordinate. But also you can also put Keplerian elements. This is example of some packages, and I will focus to this one today and for you. It is written in previously in C, not B, not A, C, and recently in Python. So we will focus on these packages. Let me explain an example. Why? Oh, it's a time lag. Asteroid 2016 H03. This is a special kind of orbit. This is a sun. This is the Earth. For rotating coordinate system means sun and Earth are locked in one AU, and the orbit of this object, a kind of satellite, kind of moon in rotating coordinate system. But actually, in inertial frame, this asteroid orbiting the sun. So we want to investigate orbital dynamics, including all planets and the moon. So you will have Mercury, to Neptune and the Moon. Why? Because it's very close to the Earth. Moon is an object separated from the Earth. We can use it. So, for example, we have a date when this value we collected. Semi-major axis, 1 pointer AU, eccentricity, inclination, and so on. 6 orbital elements. Also for the Earth, for the Sun, and other planets, and the Moon. So we have 8 planets, 1 Moon, 9, the Sun itself, 10, and the asteroid, 11 objects. This is the orbital element for this object only. We have also for the Earth, Mercury, Neptune, Jupiter, the Moon. How about the Sun? So we assume the Sun is in orbital element 0, 0, 0, all zeros. Okay, at the center. So what? Why? Propagates very slow. So this object, the orbit of this object is what we call as retrograde satellite. A kind of satellite encircling the Earth retrograde. We use packages, 2 packages, Mercury and Swift, the perturbers, integration step, for example, 1 to 100s, 1 to 200s, for 10,000s, the short. Is this short? It's really short. 1 million long years. So what we have in the past, 20,000 years, and the future 20,000 years. So you have a kind of pattern here in spatial parameter. I will explain later. Parameter derived from these 6 orbital elements. So also for the distance. This is in radian. Pi radian means 180 degrees minus 180 degrees. So all of this one circle, 0 to 360 degrees. This is the distance from the Earth. 6 times 10 to minus 3 minus 6 10 to minus 3. 0.0001 outer from the Earth and the inner part of the Earth. So the object, once for very short time, close to 0, close to 0, close to 0, close to 0. Close to 0 means retrograde satellite, like what we saw in now, such as like this. And for HS, like this. So it's kind of alternating retrograde and horseshoe types. For it is an example. We can know, we can result this. For example, another one, the same object, but we want to know the quasi parameter. it's locked in a resonance or not. So we can say here the value of the parameter variate for 1,000,000 years. For a million years. So this object is not in a quasi-lock resonance. From dynamical study, we can know in the future this object will be not in resonance, in quasi-resonance. How about the energy? If we plot eccentricity versus argument of pericenter from 0 to 360 degree, eccentricity from circle to 0.6 eccentric, we will have a kind of topography. If the object fall into this region, the object can only have very limited value of argument of pericenter. If the object fall in this line, so it can have value of small omega freely from 0 to 1 circling. So the red dot here is the object itself. The object itself is not in quasi-resonance from this diagram. No, can be here, can be here, can be here for a million years. If, for example, the black dot fall in this region, we can say at that time the object fall to the quasi-resonance. Another one, comet. Comet C 1999 X3. We examine for 10,000 years. Near Earth comets. Comets residing close to the Earth or dynamically related to our Earth. Probably in 2,000 years from now, the orbit will change, and also for other objects. This is for example. How do we know? Once again, we collect data. For comets, we have actually 6 because it can be changeable. A and Q, perihelion distance. This is nominal value and this is uncertainty of this value. For example, eccentricity close to 1. Very, very eccentric object, a very eccentric orbit. 0.98. Small inclination, 2.6 AU from the Sun. Using the same packages for all planets and the Moon with steps 1,000 or 1 to 500 years. This is the numerical method. This is a non-gravitational force. This one. Non-gravitational force, as I explained previously. From the comet ejected out some mass. And this is one for the relativistic correction. Why? Because the orbit very, very close to the Sun. We put the relativistic correction when the object very close to the Sun. Very close, even Mercury orbit. Close to the Mercury orbit. This parameter for outgassing, cometary outgassing. So what we have? Allah. The green one, you see the green one for the left side of parameter. On the right hand side, you follow the blue one, the purple one, and the orange one here. So you can see here the eccentricity will be parabolic and very, very close to the sun for 2,000 years. How about the quasi diagram? It's the same as before. So the object is for 2,000 years in this cross, black cross here. It's not in quasi resonance. The upper part, very close to eccentricity of 1. Without outgassing correction, this is with outgassing correction. You may see the blue variation here, different from the if we put outgassing correction. And also for the inclination. How if we put the relativistic correction? More or less the same. More or less the same. Between without correction and with relativity correction. Now, so I made 3 models, the red 1, 2, and 3, and all of them, many objects mimicking the comet, 1,000 objects for each model, and integrate for more than 2,000 or 3,000 years from the epoch, we will have that number of objects decreasing and become 0. This means that all objects belong into the sun. That is the reason why this comet is classified as sun-grazing comet. Sun that one time in the future will plunge into the sun. 2,000 years from now. Very small number survivors. Thank you. The next one, I will, together with you, you may use your laptop or with the internet connection. You will have this assignment. I will show you how to collect initial values. Select the trans-Neptunian object, Plutinos. Maybe some of you know. Plutinos, simply object very similar orbit with Pluto. About hundreds objects. So we want to select the Plutino, for eccentricity, more than 0.5. If you want all of them, you can choose also. Then you conduct numerical experiment using rebound for 100,000 years, for example. But you should include all planets from Mercury to Neptune. Display your result and explain. I hope I should stop. Can you type this link? You can use your Google search with GPL NASA Solar System Dynamics. If you don't want to type this, you can join for two site ssd.gpl.nasa.gov. You will have stop share. Mana ya? Like this? No. You have it? SSD. Okay. Some of you probably. Now, the next step, you can click this link, query, small body database query. Okay. You will have 4 pull down menu. Okay. Now I want to explain one by one. Limit by object, kind or group. For example, you want just only comet. You select just only asteroid. Limit by object. You can click the plus. You click the plus. You will have this. Okay? What kind of near Earth objects? What is this? Potentially hazardous asteroids that you want to nuke. Potentially, not dangerously, not certainly will hit the Earth. Potentially hit the Earth. Group, all object. Asteroid, comet. Numbered means the object has number or not. For example, previously I see asteroid 2016 HO3. This asteroid has not been numbered yet. Fragment, comet split, or satellite. So you can choose asteroid, for example, or comet, yeah, all objects, if you want to asteroid and comets. Okay? Now, limit by orbit class. What does it mean? It's many classes. Many classes. Previously, Apollo, Amor, it's a class of near-Earth objects. This is a class of asteroid that crossing orbit with Mars. Main belt, outer, Jupiter Trojan, Centaur, Trans-Neptunian. You should click here. Trans-Neptunian object. Comet? No. You just click Trans-Neptunian object. Okay? Next. Please careful here. Custom object orbit constraint. How do we know the Plutino? Okay. Physical parameter, such as if you click physical parameter, too complicated. Diameter, albedo, rotation period, for example. No, we don't use this. Use the last one, orbit and model parameter fields. The lowest one. Okay? Select field orbit. You can collect now. You can collect eccentricity, semi-major axis, inclination, and so on. Okay? Eccentricity. Click the eccentricity. E. Select operator. More than or equal to 0.5. You click, you type 0.5. Type 0.5. Is there any trouble? You type eccentricity more than or equal to 0.5. Okay? Click add constraint. The green one. Add constraint. You now have trans-Neptunian object with eccentricity more than or equal to 0.5. One orbital parameter. We should select the other 5. Select again orbit and model parameter fields, but now you select A, astronomical unit. Operator, range. The Plutino, you should type 39 to 40 range. You have two boxes here, 39, 40. Then 39, 40. Add constraint. Click again. Add constraint. Now you have two selected orbital elements, eccentricity and semi-major axis. If you type wrongly, you can cross here. And retry again. Okay? Now we will have inclination I in degree. Do you know the suggested value? More than 0. More than equal 0. Okay, add constraint again. So we have 3. Now, what next? Field node, longitude of ascending node. 0 to 360 range from 0 to 360. Add again constraint. Yeah. Okay. Check. Limit origin. Oh, okay. Okay. Oh, okay. The first one, what is? Limit object class, okay. Limit object class, you just choose asteroid. Limit object group, object class, just trans-Neptunian object. Okay, only a single click here. And the second question, how can we put 39 to 40? This is an information for you that the Plutinos should have semi-major axis between 39 to 40 AU. Because of what? Because this region is an interplay region between the objects, the trans-Neptunians inside this range, with Neptune. You may know that Pluto has an interplay playing with Neptune. Maybe you know. Today they are still playing. Playing. Yes, it's from references, many references that the Plutinos orbit have semi-major axis between 39 to 40 AU. Okay, let me continue. We again select these fields. Now Perry, argument of Perry center. Okay. Argument of Perry center. Again, this is one circle, 0 to 360 degree at constraint. So we have 5. So the last one is, you may know, the last one is what we choose? Mean anomaly. M operator, okay, same. Mean anomaly has range between 0 to 360. Now we have all 6 orbital elements for Plutinous only, right? We do not have planets, do not have yet. Okay, it's only the Plutinous. Okay, now output. This is asteroid basic, apply, okay. If you want to choose apply, that's okay. Simple. But too many. Output field. You don't, just 6 you want to select. If you want to know the name, it's okay. A, E, eccentricity, inclination, not very. But you do not need this one. Probably you, for now, for simplicity, you just take, then deselect. You just only 6 plus, maybe you want to know the name of the object. Right? So deselect the others from small key to H, large H. Okay, the first step in this part, you just click apply, asteroid basic, then the output field, you will have many entries here for outputs. What outputs do you want? Actually, we only need 6. Mean anomaly you don't have? Oh, I missed one. Where mean anomaly? Where the mean anomaly? Oh, you should put here. Mean anomaly. Add. Add. So you have mean anomaly at the bottom. Okay, I back to the we have this, right? 6 orbital elements. If we select basic for asteroid fly, there is no mean anomaly. There is no M. You don't have M, mean anomaly. So you take the M from available fields, check and add to the right one. Now you deselect the many checks is here, deselect, remove, sorry, not deselect, remove, up, down, remove. So finally you have the 6 and you want to know the name of the object, ID of the object. Okay? Now get results. Click get result on the left bottom left. So you have only one object. Oh, is it true? Inclination more than 0, eccentricity more than 0.5. You have only one object. Okay? Is it interesting or not? Only one object. How about if you want to put some other objects? Okay, for example, you change the eccentricity. Okay, click the cross, delete eccentricity, then select again with eccentricity more than or equal to 0. Add constraint. Eccentricity now at the bottom of this set. Okay, it doesn't change. So we again click get result directly after we change the eccentricity. So what we have 550. Wow. You can imagine how long the computation time. It depends on the processor you use. Too many. Okay. Now you change the inclination. Change. Now the inclination more than or equal to 30 degree, for example. Add constraint. Now the inclination at the bottom of the set. Get result. How many? 33. Yeah, appropriate number. Yes.
I have a question for part in custom object or auto constraint.
Yes.
Are there default constraint, or maybe I want to ask if we not at Perry M and node constraint, are there any default constraint or not?
Oh. If you need not to put the Perry node without constraint, yes, it's okay. Let us try now. Node, we don't need that. Perry, M, centricity. Okay, just 3. Okay, how about the result? Same? Same. Yes, you're right. Just to constrain, if a full one circle, 0 to 360, there's no constraint at all. Eccentricity, it can be hyperbolic. The eccentricity For example, 1.2 more than 1. Okay. Do you want to simulate or integrate the 33 objects? Now you should get the data. How to get the data? Where? Huh? Download the CSV format. Okay? Actually, you may change the eccentricity value or a constraint of the eccentricity, inclination, as you want. Or even no constraint. But you should constrain the semi-major axis. If not, you probably have how many TNOs? Not today. 3,000? 5,000? No, 3,000 TNOs. So you computational time will be long. Okay, any questions from you? Or is there any question? Okay. How about the planets? There's no planet for choice here. There's no planet. How about the planet? It is very important. You should know one entries you should know beside this 6 plus name, the epoch. The orbital elements, these orbital elements are calculated at what time? Not today. You should put other constraint epoch. There are 3 epoch. Yeah, for sake of simplicity, just click this one or this one. You want to epoch, that's okay, or epoch MGD. Okay? Add again epoch. So you now click get results. You know the epoch. Whoa. You face a trouble here. You face trouble. These elements only can be used for this epoch. This element only can be used for this epoch. So you have trouble when you run all together, but you have different epoch, different configuration. Okay. Is there any same epoch here? I suggest you choose epoch as constraint. Okay? Where? Physical parameter, object field, orbit. This is any epoch. Mana epoch? What in here? No. It's no epoch. MNTD, TDB, period, Jupiter, Sigma, no. Okay. Now, if you face this problem, simply from this 33 object, you just select for the same epoch. For example, after you download the CSV file, you just remove other epoch. So actually, you will have small number than 33. Same epoch. Okay? I don't know how many. How many? 20? About 20. About 20 objects. Okay? Now, you make a note for the epoch. MGD 59800. Okay? Now, okay. You back to here. Now you click the horizon system. Mercury to Neptune, you will collect 8 data. Okay. You choose the second menu, app, horizon system, app. Now, carefully, you select this. If you want to observe an object, you should click observer table. But now, you do not want to observe, right? If you want to Cartesian coordinate for planet, select vector table. If you want to Keplerian orbital element, you choose this one, osculating orbital element. Okay? Osculating orbital element. Then, target body. What body do you want first? Huh? Mercury? Oh. You do not want to You want Mars first? Okay. I want, for example, Mercury. Okay. Search. Is there any more Mercury? No. Yes, there are two. You had better to choose Mercury barycenter for accurate value. But if you want just to exercise, you may choose Mercury. But if you want to accurately output the value, you should click the barycenter. But consistent. If you choose the barycenter, you should choose other planets also at barycenter. Okay? Barycenter. Select indicated body at the bottom. Now target body Mercury. Coordinate center, Sun. Okay, that's okay. Sun as body center. Time. Oh, edit. Number 4, time specification. Oh, look. Wow. Oh, is there anyone to know the 59? What is MGD? 59 59800 is equal to calendar 59800. You should transform the 9 August 2022. Oh, sorry, 09. Stop time. You should better choose 1 day because you just need one data. Okay, from 9 to 10 August 2022. This means for step size 1 day, you will have 2 data for Mercury. But actually, you just choose the first data because the interval you cannot use 0 days. You cannot use 0 days. Use specified time span. Oh, oh, why? Okay. Now, number 5, edit table setting. You should this. Okay. You should choose this one. AU for distance, days for time as a unit. AU, the same as semi-major axis, unit for the semi-major axis in AU, and time in days. AU and days. AU and days. If you want to know the properties of the planet, you can click this one. If you do not want, just leave it. For example, Mercury has a radius, Mercury has surface temperature, Mercury has, okay? CSV format? Okay, use specified setting. Now you generate ephemeris just for Mercury. This Mercury has mean radius. This is the properties of the Mercury. Mass ratio Sun to planet, moment of inertia, mean temperature. If you do not want this information, just leave it at table setting. Object summary. Okay. From 8 August, from 9 August to 10 August. You will have the same number, okay. Oh, sorry, 0.5. Jadi kurang 5 ya? No. Point, oh, okay. So, you will have here EC, PR, IN, PM, and so on. This notation, you should know from this one at the bottom. EC means eccentricity. QR means periapsis distance. IN means inclination. So, what we want to know, semi-major axis. Or else, eccentricity, inclination, longitude of ascending node, argument of perifocus or pericenter, mean anomaly. But we cannot deselect others. So we collect all of them. Yeah. Download result. Now you have Mercury. You repeat for Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Now you complete. Now you complete the initial value ready to conduct simulation at rebound. You have Plutinus, 32, 20, about 20. And then you have 8 planets, about 28 objects with the same epoch, 59800. Then you put the values, all of the values to rebound, and you run it for 100,000 years. Is there any question? What?
Yes, yeah. So
Yes?
in this, hello sir. So first, good morning. So in this, when you search for the planet, so in this file, if you see the epoch is 59800.5. So will that make any difference? Because when we search for the that small database query, we were like exactly 59800.
Oh, okay. Previously, when we select the Plutinus,
Yeah.
we use MJD.
Yes.
MJD. MJD.
Yeah, MGD.
This means modified
Julian date.
Julian date. For planets, we have GD, Julian day number, GD. That is 25 245,980.5.
Ah, yes. Okay.
Yes.
Yeah. Okay. Yeah. Got it.
Previously at Plutinos with MG day we have 59800.
Okay.
Right?
Yes. Yes.
So there is a relation between J day and MJ day.
Okay.
That is MJ day equals to J day minus 24,000,000.5. You can find in literature that modified Julian day is equal to Julian day minus 24,000,000.5. It is a convention because if we write in J day, many digit we use. So for simplicity, we can use MGD. MGD equals to GD minus 24,000,000.5. So MGD 59800 is actually equal to GD 245,980.5. So our data is consistent. I hope this satisfies you.
Yes. Yeah. Thank you. Thank you for the clarification. Yeah.
Is there any? Oh, you too.
Would the dynamics of the loss change if we take the full step? So, I think full set of subset. If we fix all of that error in the calculation, is there an impact to the?
Oh, I see. Okay, good question. In this occasion, small solar system bodies, we usually neglect gravitational attraction among small bodies. So a small body has perturbed from main bodies only. Main bodies means planets and of course the sun. Among main bodies, yes, they have gravitational attraction. But among small bodies, there is no gravitational attraction. It is assumed. So a small body perturbed a small body is perturbed by all planets and the sun. But among small bodies, there is no gravitational attraction. It is assumed like that. And small bodies do not have any gravitational attractions to main bodies. It is also assumed. So a 10O cannot 10O do not perturb a planet, but a single 10O, of course, is perturbed by a planet, all of the planets and the sun. Okay, is there any question or comments? You can practice the taking the data first, and then I don't know about the groups. There's any several groups probably has been okay. So one group consists of how many people? 7? 7, okay, 7. Among the 7, you should compromise. I want to inclination more than 2 degrees. I don't know. I want to more than 90 degrees. So you should make a convention first. The parameter do you want to type in for selection of the Plutinos? Is there any question again? Yeah. Yes. You understand. But for special installation task.
See, if you use Windows 10 or 11, there is a Microsoft Store, and you can download Ubuntu here, and you can install the WSL first. Then you can just Google it how to install Ubuntu in the Windows. So actually, it's Ubuntu run Rebound, not Windows.
Yes.
So Windows.
You need the bridge.
Yeah.
You need a bridge by using
Ubuntu based, but actually Windows based on the layer Ubuntu, then you can install Rebound at the Ubuntu, some kind of that.
Because we can use full of power of the computer, not divided like in components.
I just know 2 months ago from you, right? Okay, is there any? I suggest you to in your group for 7 people, check one by one the initial values. You should select the right ones before you run the rebound, run the simulation for 100,000 years. Initial values are important, very, very important. As a note, you just use this one. you do not use this one, the same epoch. Only a single data set for one planet. Technically, how to put the initial values, you may read the file. You just what? Put the initial values in a file, then the ribbon will read this file. It's very convenient way. It is difficult for you? No? A group of 7 people, I think you can discuss more intense. And even 2 other groups. It is not it's not a test. No, it's an exercise. Is there any question in 23 objects? Oh, okay, just cross check. Okay, thank you. Oh, great. Is there any question in YouTube or no?
Is it difficult for you or no?
No. You can do that. Participants.
Just an exercise if you want to run and display the result, and you can see as interesting pattern. Interesting pattern.
Okay, so thank you very much, Dr. Budi, for the nice talks. We will make again in laptop, yeah, the one, and then please do your assignment. You can discuss with your group, and of course you can also ask your tutors or Dr. Budi for if you have a question. Okay. So for the last part, we will have a photo session. Oh.
Okay, please open your camera. We will begin the photo session right away.
Oh, but us, we are still here or
Okay, is everyone ready? Oh, kameranya mau ke ini. Pak Budi nggak kelihatan nanti ke sini. Enggak, Pak. Pembicaranya nggak kelihatan. Oh, Pak Budi mau ke sini.